Hey everybody, this is Jason with Isn't Life Curious and Curious About Cannabis. Thank you so much for tuning in once again. Today, I'm really excited to be joined by Twinkle Paryani from Abstrax Tech to talk all about how to study the aroma of cannabis and kind of better ways to be testing for terpenes and all sorts of other things that we have to unpack. And really resulting from a study that Twinkle published very, very recently that's got all sorts of cool little findings in it that, I mean, there's like three or four or five like very different takeaways from the study that are cool to cover. So Twinkle, thank you so much for being willing to come on the podcast and chat about cannabis science today.
Absolutely. Thank you for having me. I'm super excited to talk about this and be on your podcast. I love your podcast and I'm excited about the Isn't Life Curious change. I think that's going to be really awesome.
Oh, thank you. I'm excited about it. Because ultimately every discussion I've ever had on this show is about more than cannabis. And so I think it'll be a nice little transition, even though there's plenty to continue talking about with cannabis. Even what we talk about today about aroma science and stuff, it really extends far beyond just the cannabis plant. So thank you. I'm excited. We'll see how this all goes. Um, and to kind of kick things off a little bit for anyone listening who's maybe unfamiliar with abstracts or your work or anything like that, paint us a little bit of a picture of some of the work you do, some of your background, and kind of how you got into studying cannabis aroma.
For sure. So my background is actually I'm an analytical chemist. And so before I worked at Abstrax, I was working in public health and I was doing metabolite research on smoking metabolites, so
Nice.
tobacco smoke metabolites. But I always knew that I wanted to work in the cannabis industry. I wasn't sure what that looked like when I graduated
Mhm.
from school because it's still a very new and changing marketplace. Um, so I worked as an analytical chemist um, with LCMS, and then eventually I worked in a testing lab in California, and then I joined Abstrax. And Abstrax is kind of a unique position in the industry. They are a flavor house or terpene manufacturer. So they procure neat materials, they purify the materials, and then blend them into products that people in the cannabis industry use for flavoring vapes or e-cigs or all kinds of different applications. But they also have committed a significant amount of resources to doing research on cannabis. And the way that shakes out at Abstracts is they have a they have a BHO facility, and so they do butane extraction. And so those two worlds kind of collide when we use gas chromatography to analyze cannabis and then use that data to improve our products for cannabis lines. But not only do we use that research to improve our product lines, we also publish that research and work with clients to do like research and development on issues that we think are important to the industry. So there's some other studies that we have coming out that I think will be really impactful. But basically Abstrax acquired this really fancy gas chromatography instrument, and it allows them to see the aroma of cannabis um, chromatographically in a lot more detail than other people. And so through that, over the last 5 years, my boss, our VP of R&D, and myself for a shorter part of that have been researching and publishing these new compounds that we've been identifying for the first time in cannabis.
Yeah, and that's one of the things that got my attention on abstracts early on was there were these interesting studies which kind of go back early on looking at like why does cannabis smell skunky and these sorts of things. But the insistence on making the research public and really doing work to educate the public on the research coming out was something I really valued and got my attention early on. And since then, there have been such a series of studies that have kind of come out that are telling this extended narrative around what we know and don't know around cannabis aroma. And then the study that you just published was kind of this like third or fourth piece of this kind of puzzle that's being laid out. This almost this like red carpet of cannabis aroma that keeps unfolding as we understand more and more and more. And one thing you mentioned is at Abstrax, you have this opportunity to employ certain levels of testing that are not commonly seen in high throughput commercial cannabis testing, usually because, high throughput commercial cannabis testing labs, they've got to run as many samples as possible, testing for, just what's needed for regulatory compliance. And so this is a very different scenario. And for anyone listening that doesn't know, most commercial cannabis testing labs test for anywhere from maybe a dozen to 40 terpenes or so. And we know that there are hundreds of these things that show up in cannabis, not to mention all of the little derivatives from terpenes that can also show up in related compounds. So before we kind of go any further, can you explain a little bit about how just the testing method that you're employing is different than what a lot of cannabis testing labs are, and just how much are you able to see in these samples compared to what most labs see?
For sure. So one of the most important distinctions is what a testing lab is doing is called a targeted analysis. So they're
Hmm.
looking for very specific compounds. They're looking for those 40 or so terpenes that they have specific standards for. And what testing labs are doing, they're using either GCMS or GCFID, which is gas chromatography. And then the last part of that is the kind of detector they're using, either a mass spec or a flame ionization detector. And those two things work pretty differently. The mass spec will tell me what that compound is, and all the FID does is record the signal as it's burned in my detector. So it's kind of a more I need other information to be able to identify those compounds from an FID. And so they are using one of those detectors, and they're using one dimension of separation, which they're separating all their compounds by boiling point or
Hmm.
molecular weight. And so if you think about it in a really simplified way, as time goes on, if we have a graph, as time goes on along the x-axis, the compounds are getting bigger and bigger and bigger
Yeah.
as my run goes on, and they're coming off later as the run goes on. And basically the chemical separating force in chromatography is the separation based on the chemical structure. And so when I'm looking at terpenes, they all have this same isoprene unit that make
Yep.
them all terpenes. And so if I'm looking at 40 different terpenes, even though they're different, and some of them might be monoterpenes, and some of them are sesquiterpenes, some of them are cyclic, and some of them are branched, they are all very structurally similar. And so with 1D gas chromatography, you're really limited by their structural similarities. So you can't separate
Yep.
everything as much as you'd want because they all kind of look the same. And so what we actually have a system that utilizes MS and FID at the same time. So I'm running my samples and I'm getting both of those detection signals at the same time, as well as a third detector, which is not used in any cannabis testing labs right now. That's called sulfur
Yep.
chemoluminescence detection. And the entire point of that detector is only to detect sulfur compounds. And it actually has very little to do with the overall chemistry of the structure. It just has to do if it's sulfur containing or not. And so our system, we already have 3 times as many detectors as a traditional testing lab. And then in addition to that, we have an extra layer of chromatographic separation because we have 2D gas chromatography, which is 2 dimensions, which means we have 2 columns in our oven. So as 1D has that um, separation by boiling point, we're doing that.
Hmm.
And then we're also additionally separating by polarity. And so we can see structural differences that are related to the polarity a lot easier than they can in 1D. So for example, I can see oxygen containing species in a
Yeah.
different
Yep.
space of my chromatogram than on a 1D. And so that signal might be completely buried to a testing lab. So there's a lot more fidelity with 2D gas chromatography. And then additionally, like I said in the beginning, we're doing untargeted analysis. And so we're seeing in our data somewhere between 400 and 500 different compounds. We're
Mhm.
not maybe able to validate those all individually, but we've gotten a pretty good amount. I would say probably close to probably between 70 and 110 compounds that we have used reference standards for before. And so I think
Yeah,
that's one of the
yeah.
biggest things. So when testing labs run a sample, they see all this data, but they're not seeing like the 300 extra compounds that are hidden in their data. They have no way to separate that and utilize it. And so we see the whole untargeted picture. And sometimes we get lucky and we can find standards for them. And sometimes we can't, and we have to just estimate. And,
Right.
everything that's been published through the papers has been has been confirmed through the use of another material, which is really important for these testing labs because
Mhm.
they are not in a position where they can't say what anything is without being 100% confident, or it puts them in a huge liability.
Right, right. Yeah, exactly. It makes it hard to pursue a lot of kind of speculative, explorative kind of research and studies and things because it's all commerce driven. And yeah, if anything happens to not be exactly correct, you can go to court over it and it becomes a whole big thing. And it's fascinating, this idea. I think it's something people don't think about a lot. Just because if you're not doing analytical chemistry, you have no reason to think about it. But this idea of the 2D situation of having two columns. So essentially, for anyone thinking about this, you have a sample that if it's going into a gas chromatograph, it's basically being vaporized as soon as it's injected into the GC. And then essentially you have this flow of the of it go into another column. And those columns can, have different programs and treatments and things depending on how you set it up. And to get all of this information, because it's true, you can have, if you just do a basic GC run, you can see a single peak and assume, okay, that's myrcene, let's say, whatever. But then if you look at it more carefully, especially under a 2D situation where you can put things under different conditions to start to parse out the things that are kind of overlaid on top of each other, you say, oh, actually, I've got 4 or 5, 6 things there that are all in varying concentrations, some of them very trace, that are all stacking on top of each other. And we've just been calling it all one thing. Um, which immediately, I mean, something that I talk about a good bit, but doesn't this immediately kind of raise some red flags in terms of how much we trust regular terpene data when we recognize that, that there are a lot of things hiding in there?
It's so hard to because as we do the research, we're learning more, like almost retroactively about how we could have done things better.
Right, right,
Like
exactly. Yeah.
we just went to ACS in Denver and I saw someone else's presentation. I'm gonna have to try to remember who it was, but they basically said like everybody has been using the incorrect version of the stereochemistry for limonene, for D-limonene.
Yeah,
Like
yeah,
everyone's been writing D plus limonene, and the only one that cannabis can make naturally is the D minus limonene.
yep.
And so it's stuff like that. I mean, even with the advanced fidelity of the 2D system, it doesn't tell me anything about the stereochemistry, about
Hmm.
chirality. And so it's kind of like we are always having to go back and rework what we've been doing. And I think that's true of any growing industry.
Yeah.
But sometimes because there's so much money, bureaucracy, people's business licenses on the line, they might be slower to go back and retroactively adapt those changes. And I'm sure it's not easy. Like I know it's not easy to
Hmm.
acquire new instrumentation and build
Right.
funding for that and have people who are capable of maintaining the system and utilizing it properly. But we are in an industry where I feel like we're slow to adopt changes. And
Yeah.
the way that in California, the way that we have the DCC, it makes it so that we have, if you were a testing lab, you have to funnel all your new changes and everything through them also and
Right.
have them validated. It's
Hmm.
not as easy as, me, I get to be in a research lab and I can make changes on the fly as long as I'm not publishing that data or needing it for something else. I'm allowed to change my method parameters. If I wanted to put a chiral column in there one
Hmm.
day, we have plans to do that eventually, but these testing labs don't have the infrastructure. They have all the right people and the right pieces, but they don't
Yeah.
have the time or luxury to dive into it
Yeah,
so
the
deeply.
system just doesn't really allow it. Yeah. And it's a shame too, because having all of these testing labs all over the country with these sophisticated facilities, which I'll point out to people, a lot of these testing labs are more sophisticated than most like analytical labs you see in most industries in general.
That's true.
Um, and so to have all of these resources, it would be nice to find a way to create some space for that R&D, for that explorative research, data sharing and things, and method improvement. I mean, there's one thing that Abstrax's work highlights that we're talking about is, there's immense room for method development and validation when it comes to terpenes in commercial cannabis testing. Because like you're saying, what Abstrax is doing is already beyond what a lot of commercial cannabis testing labs can really rationalize doing. And then you're also recognizing, well, there's more we can do, and there's more that, that we plan on adjusting our methods and going further. Um, so, and people care. Like the terpenes are such a big focus of the industry's attention right now. Um, And I know from working in dispensaries and consulting with patients, we've traditionally had the THC kind of data chasers, and now there's sort of like the terpene data chasers. A lot of people are looking for terpene data when they're trying to make purchasing decisions. So trying to ensure that data is as accurate as possible um, would definitely be nice. The chirality thing is kind of an issue that also affects cannabinoids. There's new data coming out showing that there was a study recently that came out that showed that there's one an enantiomer of CBC that is an agonist at CB2 receptors, and the other one isn't. And so it's like, well, when we talk about CBC, like, what CBC do you have? Is it plus or minus? And so all of these things are super interesting. Um, to back up a little bit, do you mind kind of telling the story, sort of the science of exotic story, a little bit of just how the kind of studies that led to your study? Like I said, it kind of started looking at kind of traditional cannabis and saying like, why is it skunky? What are these sort of like depths of smells that we don't really find in just sort of I don't know, kind of the terpene blends and things that were kind of going around at the time. Um, yeah, tell us a little bit about kind of how that all unfolded.
Yeah, so some of this research started before I joined Abstrax, but I'll just give a good summary of it. So basically, the first question that they knew that they really wanted to tackle when it came to aroma chemistry and cannabis was, yeah, where is like gassy or skunky smelling cannabis come from? Abstrax being a terpene manufacturer, they were used to dealing with a lot of these compounds that were endogenous to cannabis, a lot of terpenes, and we're used to dealing with them in high concentrations, and none of them have ever smelled the way that we know skunky cannabis to smell, like the dank, sulfurous nature that
Mhm.
really lingers and sticks to everything. None of the terpenes really have that effervescence. And so they knew it was something beyond a terpene, or at least that had some kind of structural
Mhm.
uniqueness to it. And so the first place that they wanted to look was for sulfur containing compounds. I think in their mind at the time I've talked to Ian, which is my boss. He's the director of R&D at Abstrax. He's our PhD research scientist. When I was talking to Ian, he kind of, in his mind, he refers to it as like that was low-hanging fruit for them because they knew that there was something there and they had a pretty good guess that it was going to contain some kind of sulfur compound. And so they were like, let's get an SCD and let's see if we can find any kind of signals in there. So gosh, and over the time since this has since that started and then all the way to now, it's so crazy to think about how far we've come.
Yeah.
Since then, I think we've probably identified, I don't even know, maybe at least like 9 different sulfur compounds. So the first wave of compounds that they discovered were these prenylated sulfur compounds, which have a prenyl group, which is similar to some other compounds in cannabis, like other terpenes and stuff. Prenylated sulfur compounds are very savory, and they're used in tandem with words like gas, funky, diesel, skunk. And so that was the first layer of what we had discovered was like maybe 7 compounds at first that all contain sulfur. And they were measuring at that time, they were using headspace injection. And the concentration of sulfur was so low in those samples that they were measuring in flower samples that what they were doing was concentrating the sample 6 times onto a cold trap before then injecting the cold drop into the instrument. So
Wow. Yeah.
they're creating a vapor and then they're depositing the vapor onto a material that's supposed to hold it there, and then they're amping up the sample concentration. So the sulfur compounds are in such low concentration, we could barely see them in flower with headspace. And then after that, we had some method changes. We decided to try to look at liquid injection to see if we could concentrate our
Nice.
samples more before we put them on the instrument, like just loading more onto the column. So then when we switched to liquid injection, we started seeing a ton of other compounds that we hadn't seen before because they were in such low concentration. So then we started to see different kinds of esters, some nitrogen containing groups, some naphthalene groups, like lactones, all these different functional groups that are technically not terpenes we started seeing in low concentration. And so the first thing we had to do at that point was try to validate some of these structures and compounds. So we went into the flavor lab, started taking all their esters and injecting them in single component mixtures onto the GC and confirming that that is actually what we're seeing. And then after we started seeing all these compounds, the next thing was like, okay, like, can people differentiate when there is this compound versus when there
Right.
isn't this
Right.
compound? So we started looking into the sensory data. And then I feel like that's really when things started to like become like kind of crazy and mind-blowing. Like it's crazy to identify new compounds and find new compounds, but when you are doing sensory research and the participants in the sensory can differentiate strains based on these minor components that we previously had no idea about, that was,
Yeah.
I think, a big game changer. So the paper that was published right before my paper, that Ian is first author on, is all about these minor non-terpenoid compounds and how they differentiate aroma. So we tested 31 different cultivars. So they're genetically different. They're procured from all different sources, and they're different strain names, commercial strain names. And so we tested them on the GC, and then we had, I believe, 12 participants do sensory on them. And what we found was things that are considered exotic cannabis, so either really sweet or really savory, something that pretty much now we know the smell does not come from terpenes. And so we created this aroma spectrum. I can share a slide so the people can
Oh yeah. Let
see.
me make sure I'm giving you the permissions there so you can do that. Gotcha. Yeah, the flavor spectrum, I love showing this because it's a nice kind of reimagining because there'd been a lot of different people sort of working on thinking about the spread of the smells of cannabis and things like that. And this one was kind of, I don't know, different.
Yeah, so Ian and I like just first of all, we're just talking about this graph on the left here, this plot on the left. But Ian and I look at a lot of like aroma marketing, a lot of aroma research. And so we are constantly used to seeing that flavor wheel.
Hmm.
And I don't know if it's just us, but the wheel doesn't always make the most sense to me or Ian, maybe for that fact,
Hmm.
like because we're because there's I feel like it is a spectrum because the wheel
The
in
wheel
theory
brings the like extreme ends to be close
together.
together. Yeah, right,
Exactly.
right.
That's exactly the point that I was trying to make. And so the spectrum kind of keeps it more linear. And as a scientist, like anything that I can simplify into a linear scheme is more digestible for my brain. And
Absolutely.
so we had this, and I think originally we just had prototypical and sweet. And as we got more samples in our lab, we had more sensory discussions about these. We realized that a significant part of these samples are not just sweet, they're also savory. And there are different kinds of savory. So basically, anything that you or we would classify on the ends of the spectrum is heavily predicated on the presence of these non terpenoid compounds. And things in the center of the spectrum, so we have the terms earthy, skunk, and spicy, are going to be what we call prototypical, but more influenced by regular terpenes.
Hmm.
And that kind of checks out if you smelled these terpenes individually and you've smelled some of these flavorants, which is what we refer to as the non-terpenoids, individually, man, you can really tell that prototypical cannabis, the smell is 100% coming from terpenes. Like it
Yeah,
smells
yeah.
just like if I pick up any random group of terpenes and smell them. But these sweet ones, they smell a lot like other fruits. They smell like berries. They have tropical notes to
Hmm.
them. There's sweetness to them that doesn't come from terpenes. There's like sourness that doesn't come from terpenes. And then on the other end, on the savory end, we have like really garlicky, very fecal. We have a lot of different kind of savory smells that definitely don't all just come from terpenes either. So Ian's paper, oh, actually, I have one more slide I can share that shows some of the compounds that we discovered in the first paper, and then I can jump into the compounds
Oh,
that we're
nice.
discovering in our new paper. So in this slide, here are the compounds that we identified in the first exotic paper. And so here we have a bunch of esters. A lot of these are esters, which they're not
Hmm.
uncommon in nature. They're found in a lot of fruits. They're found in other plants. Really, a lot of different natural products contain these compounds. So it's not unheard of that they would be in cannabis. We just didn't know that they were there because they're in such low concentration. When you're focusing on terpenes, which are 90 to
Yeah,
95% of the aroma fraction by weight, you're drowning out everything else. And the nose is a really sensitive detector. So the nose can pick up on it much easier than some analytical equipment, actually, if you're not looking at the right
that's right.
concentration levels. So I think one of the more interesting groups of compounds that was discovered in Ian's paper was these synechioates, because some of them hadn't been reported before, maybe ever. And we actually synthesized some of these in-house to be able to test them on the GC for confirmation.
That's
So that
awesome.
was just really unique because I had never smelled anything like these synechioates before, and smelling the synthesized neat versions was really wild. And then the tropical citrus is also another really important part that was discovered in that paper. Those are a different category of sulfur compounds, where if before the prenylated ones I was talking about, the skunky ones, those are going to be on the savory end of the spectrum. And these tropical citrus ones, they are probably going to be more on the sweet end of the spectrum. Depending on the concentration and the other components, I could see them still being savory on the savory end, but usually these have like a tangerine,
Mm-hmm.
tropical, kind of citrusy and pineapple-y kind of feel to them. They're very like astringent also. Um, and then in the first paper, we identified for the first time indol and scatol, which is interesting because they're nitrogen containing compounds. And
Mm-hmm.
so this was the first time that we had really come across these kind of compounds in our data. And also these other nitrogen containing compounds up here, these fruity floral ones, which have a
Yeah.
totally different aroma than the chemical naphthalenes. But basically, Ian's paper, we looked at, this graphic on the right here. We looked at a spectrum of cannabis that was genetically diverse, and we found all these diverse compounds in them. And so then the thing we wanted to look at after that was if we look at a group of cannabis that is genetically similar, do we still see diversity in
Mm-hmm.
their aroma compounds? And can we differentiate aroma based on these compounds for similar cannabis products the way that we can for very diverse cannabis products? So it's kind of like we discovered the big picture, and then
Right.
now it's like, can we zoom in a little bit more and see if it's still applicable?
Yeah, I love that. I love the idea of like we just sort of shotgun looked at all these different things. Now let's look at these things that should roughly all be the same and see what we see there. One thing I wanted to ask you real quick on the Senecuates. I know you have the fusel sweet description here, but how would you describe the kind of overall smell of those? Is that kind of that sweet gasoline kind of
Yes, they definitely have like an alcoholic or maybe even like phenolic or
mm-hmm.
solventy kind of smell to them. A
Yeah.
lot of them remind me of notes that I would smell if in rum or something that's like
Mm-hmm. Mm-hmm.
sweet and alcoholic. I think
Yeah, yeah,
they're,
that kind of fermented yeah, yeah. Okay.
yeah. I definitely think like the word that I can pick strongly is like alcoholic. They are, and they also can be kind of intense, like as far as like odor activity, like
Mm-hmm.
they're kind of loud also in the
Yeah.
neat forms. um but that's one that we see in really 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 low concentration, so it would be cool to see, to eventually find something where they are in a higher concentration and then see how that affects the
Mm-hmm.
overall aroma, because I think right now they're kind of they just add to the flavor, but they're not like a dominating um compound the way that the sulfur compounds tend to dominate the rest
Mm-hmm.
of everything.
And they kind of remind me a little bit of some of the aldehydes, just with that ester thrown in the middle of them. Um, it's I don't know, it's interesting seeing the similarities in some of the structures. Especially I love also seeing, before we move on, I'm glad you pointed out the similarities between the indoles and the fruity floral compounds that you have up here, these three, the methyl anthranilate, the ethyl anthranilate, and the dimethyl anthranilate. Because if for anyone looking this or listening, for those listening, imagine if you know what the indole or scatols look like, they're these heterocycles that have basically these two rings sort of next to each other, one big ring and one sort of mid-sized ring. And the anthranilates basically have that side ring blown open. So it's kind of, they're actually very similar, even though at first glance they look different. And it's just that side ring is open and you've got some slight modifications because of that. So there's, yeah, very, very similar geometries, I guess you'd say, between a lot of these things.
Yeah, and that is part of what makes the analysis tricky also, is that they do look
Mm-hmm.
very similar, and that can be tricky. And the methylanthranilate and the dimethylanthranilate, I can't remember about the ethyl right off the top of my head, but those are both grape flavored or grape scented compounds
Oh,
that
okay,
are
okay.
found in grapes naturally. And they are like, if you've ever smelled like artificial grape
Mm-hmm.
sweetening
Yeah,
flavoring,
yeah.
it smells just like that in its concentrated form. So it's not like these are things that we don't already have experience with in our day-to-day lives either, which I
Right.
think was probably like one of the cooler things to me, was like, wow, these things are all around us already. But, I never, well, I'm sure a lot of us
Right.
never think that deeply about, is it in the grape cannabis that I'm smoking?
Right. And it just it brings this whole thing around that, when like grape for instance, grape headband, the strain I actually had not too long ago. When someone's like, oh, does it actually taste like grape? Is there any sort of connection there? And it's like we're getting to that point where we can say, yes, actually, there is. Like literally the same compounds from grapes are in this thing potentially, if you're able to see them. So that's just fascinating. And then we didn't really talk about these creamy sweet compounds. I wanted to make sure to mention those too before we go to the next study. So um, these are kind of mixtures because you have this pyrone and then you have these butyrates that are kind of part of that. But would these be some of the like cakey, like some of these aromas that you see in like papaya cake or other things like that that have that creamy sweet label, or is this kind of something different? Creamy sweet label, or is this kind of something different?
What I've seen is creamy and baked goods type
Mm-hmm.
smelling things are a lot more complex than you might think.
Yeah.
Just from a let's talk about it from a flavor blend perspective. When the
Mm-hmm.
flavor chemists are trying to recreate those, they are there are some of the more challenging ones. I think that honestly, like in cannabis, a lot of those smells come from the sweetness and maybe like memory association.
Mm-hmm.
And so I can't say for sure if these phenethyl compounds, like what they are in their isolated forms, if they're cakey or sweet. I know that there are some of the esters that are just like super sweet, and I think varying concentrations of that kind of push it either more towards,
Mm-hmm.
depending on if they have fruity things, it'll be more fruity. And if they have more of these creamy sweet things, and then also other compounds like lactones, which are creamy, that
Yeah,
those
yeah.
are in dairy products naturally, they might be pushed towards dessert then.
Yeah, yeah, that's a really good point. Cool. No, that's awesome. That's enough of my drilling down on all the details here. I wanted to make
Yeah,
sure to kind of hit all these categories. Super fascinating.
cool. Okay, so we looked at this in all those 31 strains. We did the sensory. We found out that there are specific compounds, there are specific esters, and other compounds that heavily influence whether the strain is perceived as sweet or
Hmm.
not. And then we took that and we wanted to do a smaller, more genetically similar sample size. So what we did was we took 5 phenotypes, which are basically like plant siblings, from the same parents, which was the strain Starburst 36 from 710 Labs. And we got 5 of their phenotypes, I think like 1, 23, 40, and a couple others. And we looked at those 5, and what we found was that there are some differences even within these genetically similar um,
Yeah.
phenotypes, that people could differentiate between the phenotypes and had different um, perceptions of them, and that there were some chemical differences. So if we go back to that density plot
Yeah.
and share it again, it'll make more sense now. Okay, perfect. So on this left side, we have this density distribution plot. And so this
Mhm.
was based on the participants who did the sensory. So the main takeaway of this is that basically the first two that we see on the screen, Starburst 1 and Starburst 40, were pretty similar, except for the fact that there was just small differences in the savory side of one of them. But basically they grouped very well together based on aroma. People thought these two were the most similar of all 5 phenotypes
Mm-hmm.
aromatically. And then we kind of see this breakdown between these two that are the most sweet and the other 3 phenotypes repeatedly, no matter where we're looking. So right now we're looking at the sensory distribution, but once we start looking into the data a little bit deeper, here on the left, this is a Pearson correlation chart that shows similarities between each of these different phenotypes compared to each other. And if you're listening visually, it basically is just one blue block, because if we're
Mm-hmm.
just looking at terpenes, terpenoids, sesquiterpenes, and sesquiterpenoids, all 5 of the phenotypes are super similar. So the lowest correlation score is 0.84, which is still a super high correlation score. So basically, if we're looking at the major aromatic fraction of these 5 phenotypes, they look almost identical to us. But we know from the aromatic data that people perceive them to be different.
Mm-hmm.
So the differences are not coming from these terpenes. So once we started looking at flavorants, we see the same striation that we saw before, where the first two, which are Starburst 1 and Starburst 40, which were supposed to be the most sweet,
Mm-hmm.
are very similar. And then apart from that, there is a varying amount of similarity between the rest of the 5 phenotypes with each other. So if we're looking at flavorants, the correlation between those two that people thought smelled the same is 0.92, which is a very high correlation. We do have some negative
Mm-hmm.
correlations, which means that they're not correlated at all, in this data set also. So that goes to show that there are some that are super similar, and there are some in terms of flavorants that have almost no overlap at all. And people can differentiate that aromatically based on this data. So even genetically similar cannabis is aroma is predicted by these non-terpenoid compounds. And in the process of that, we also identified and were able to confirm a 4th tropical volatile sulfur compound, which we named Tropican and sulfur compounds. We were able to identify a 4th one, which was the largest one in the family that we've identified so far, 3-mercaptohexyl hexanoate. So this family of compounds, they're naturally found in things like grapefruit, they're found in wine, they're found in grapes. They are sometimes responsible for off notes in beer products. They're found in hops. A lot of these naturally acidic kind of tasting or feeling fruits that are very citrusy have these compounds. And so finding another one in cannabis was just really cool, because it's like, wow, we're not just getting part of this role it took. But the 2 sweetest cultivars, the 2 sweetest phenotypes were the only 2 out of the 5 phenotypes that did not contain
Mm-hmm.
indol. So the lack of indol, it appears, had them perceived to be even sweeter than their counterparts that did contain indol. And Indol is kind of got like a mothball-y scent to it. So it's not that surprising to me, but Indol is used in a lot of fragrance and perfumes and stuff to have like a floral sweetness. So it was interesting to me that it wasn't in the sweetest ones. And what that means to me is that the sweetness of those two samples can be attributed to the other components that are in it, like some of
Mm-hmm.
those esters, and also these two had a higher concentration of the Tropican sulfur compounds than these three with Indol. So it's almost like they have an inverse relationship with Indol, where the sweeter ones had more of these tropical VSCs, and the more savory ones had less of the tropical VSCs, and they had this Indol. So that kind of gives us more information about how these different layers of compounds
Mm-hmm.
push the aroma towards one side of the spectrum when they're included at the same time.
And it makes you wonder too about like the synthetic pathways for these things in the plants and the overlaps between them. Because if it's kind of going one way or the other, that tells you there must be there's some sharing going on in those pathways, most likely, that
Right.
you've kind of got to, the plant kind of has to put its energy into one or the other, but it can't necessarily, or just maybe we just haven't seen the example of it yet where there's the balance between them, but definitely raises some very interesting questions about how these things are
Right.
made.
Exactly. I think that's like the next biggest question is like how and why.
You're
uh,
right, right.
but I think it's so cool because um the fact that these were all siblings that were grown in the same way, processed into hash the same way, like if there had been, it just there's so many questions. They were in the same environment, so I feel like we're so close but so far from figuring these things out, but it is really interesting to think about the inverse relationship and like why would a plant turn that on or turn it off?
Right.
And the fact that these other three phenotypes that have indol still contain TCSCs, it's like, okay, the plant can make some of them, but at some point it had to divert energy into doing something else. And another thing I think is interesting is that indol and TCSCs are some of the like most odor active to you,
Mm-hmm.
like sensory wise, you really detect them in low concentrations. As a person, you can detect them, and once you know what indol smells like, you can like really pick it out.
Mm-hmm. Mm-hmm.
um the same thing with scatchol. So it's just interesting to me that like these high odor activity compounds like may share some kind of internal chemistry there also.
Yeah, yeah. Super fascinating.
And then I think the last interesting thing that came from this paper was totally unexpected. So we had these two, Starburst 1 and Starburst 40, that everybody thought was like
Mm-hmm.
super sweet, super tropical, fits the description of what Starburst strain characteristically is supposed to be, a tropical, fruity, sweet candy kind of flavor. Um, and what we discovered was that some of the participants in the sensory felt that um, two of the other phenotypes that were considered in the savory
Mm-hmm.
subsection had cheese notes to them. And so I actually did not have any cheese descriptors in our check descriptor list. And so people wrote these into the free response because they were like,
Nice.
there's cheese in here and you didn't have cheese on here, but I smell cheese. So you need to know that I smell cheese. And
That's
I'm
a
so glad.
strong anecdotal evidence. Yeah.
Yes.
Like,
So I then was perplexed. I was like, she smelled cheese. Like, this is a tropical cannabis strain. But what did I do? Of course, I would never shame anyone for their nose. So I went back into the data and I looked for things in the data in those specific samples that people reported as cheesy that was different from the other samples that weren't reported as cheesy. And there was something there that I could barely see. There's these two medium chain free fatty acids, octanoic and decanoic acid, which are found in cheese naturally. They're found in blue cheese, they're found in all kinds of cheese. They do have kind of like a moldy, musky
Mm-hmm.
aspect to them. That's the part of cheese that they give instead of something like super cheddary. They kind of have like it's more just like a musky, moldy kind
Mm-hmm.
of smell. But that's another one of those things where your brain smells that and it's like, where have I smelled that before? I've smelled
Right.
it before
Yep.
when I smelled cheese, so it
It's
smells
a
like
good
cheese
thing.
to me.
Yeah.
Exactly. Um, and so we found octanoic and decanoic acid in one of the samples that was described as cheesy. Unfortunately, like the chromatography doesn't really allow for us to quantitate that. So we were able to confirm them, but not accurately quantitate them, which is fine for the time being. And so then we were like, okay, octanoic and decanoic acids are cheesy, but what else could we hypothesize is contributing to the cheesiness of this cannabis specifically? And what we found was two different compounds that we previously reported and had talked about, 2-heptanone or methyl amyl ketone, and prenylthiol, which was one of
Mhm.
our savory VSCs, the one that smells more skunky and gas-like. So, you know, based on the evidence, and we like recreated some of this data with blends, we are going to hypothesize that those two acids and then potentially other acids in the same category are what drive cannabis towards the blue cheese smell specifically,
Mhm.
because it was clear from the feedback that one was more of a blue cheese and one was more of a regular kind of yellow
Mhm.
cheese, cheddar cheese kind of smell. And so octanoic and decanoic acid are found in blue cheese because they're a byproduct of the inoculation and the process with the bacteria. So it made sense that that one kind of fit the pathway for blue cheese. And then this methyl amyl ketone is actually also found in a lot of cheese products. Um, on its own, it smells kind of sweet at a high concentration, but if you dilute it and
Mhm.
use other things with it, it does have a kind of cheddar cheesy smell to it. So the addition of that methyl amyl ketone and then a savory VSC, specifically prenylthiol, kind of push it more towards cheese than tropical. And so we propose these two different pathways for two different kinds of cheese smells based on the data there. And we're hoping to get more cheese cannabis in our hands so that we can validate this or verify this or research more to see if there are more compounds that we didn't identify. But the cheese pathways was something that was kind of unexpected in this project, because when you think about tropical, sweet, exotic cannabis, you don't
Right,
expect there
right.
to be cheese. But now that this paper has been published and I've been talking to people when we go to conferences and stuff, um, I'm finding that a lot of times tropical strains do come out cheesy and vice versa. Cheesy strains come out being more
Mm.
sweet than anticipated and being really sweet and tropical. And so, you know, there might be some kind of chemical reason why these tropical strains produce these compounds that then could push them to cheesiness in the
Well,
right concentrations.
and wouldn't it be fascinating to be in a future where if you're, breeding, hunting, whatever, that that if you're growing out a line of plants, that not only do you have some sense of the statistical possibility that you're going to see varying cannabinoid ratios or whatever when you're breeding, but also statistical possibilities of different aroma profiles that you could actually predict. And you could say, okay, if we're going for these tropicals, we're likely 25% or whatever is likely going to, end up having a cheese smell. We might have some that have this, and all related to, again, sort of the overlap of these biosynthetic pathways, the genetics behind them. There are so many research questions that open up from all of this, but this also leads into A question I had for you based on your research, in your paper, you mentioned, um, one, like you've already pointed out, a lot of producers and dispensaries and things focus on those top 3 or 4 terpenes. And that's what they put on the labels. And it's obvious that, that's not enough for consumers, and that they can tell that, things can have the same dominant terpenes, but they're going to smell different. There's different effects and that sort of thing, which then kind of brings us back around to where a lot of researchers were in the early 2000s around this idea of chemotyping, of like, how do we use the chemical profile of these products to better classify them? And that project sort of got stale for a little while until now, as we're getting this more expanded look into the chemistry of these products and partnering that with these sensory panels. So what does this mean for sort of the future of trying to breed and find unique products, that sort of thing? Because it really revives this effort of like, oh, maybe we can start to look at data. Maybe we've just been looking at incomplete data or the wrong data, and now we've kind of got a better sense of things we need to focus on.
Yeah, so it's interesting to me, like as scientists, we want a good classification scheme more than we want like anything else. Like I feel like if I
Yeah.
asked like 10 different scientists,
Give
they'd
me
be
the
like,
box to put it in.
they just need to know exactly. And um I just think that's so interesting because one of the like there was a paper that came out around the time that Ian's paper came out by Nick Jacombs
Hmm.
by at Leafly that basically showed like the classification scheme that we were using to classify effects based on aroma didn't have a
Hmm.
ton of statistical relevance except for things that were terpinolene rich.
Right.
That was like the one that was the one terpene that was chemically distinct from everything else as far as the data goes. And I thought that was really interesting. And after that, I had kind of given up on a good classification schema. I was like,
Hmm.
well, that was our last hope. Like,
Yep. Yep.
but now with this new information and hopefully like as we get to keep chemotyping these products and building out our database, I would like we've already had some breeders come in contact with us. I think the biggest limitation is like getting these testing results into the breeders' hands. Like
Hmm. Hmm.
there it is so challenging right now. Hopefully in the future, like in the next year or two, we'll have ways for people to test their own VSCs with their
Hmm.
own testing labs. And I feel like unfortunately until then, we're kind of stuck doing the thing the same way things have been done, which is using our nose, like using our human detector.
Yeah.
But what this does provide us is a route to be doing that with more specificity and accuracy. So
Hmm.
now, now previously a breeder might have smelled something and loved the way that it smelled unique and then went and smelled all their other crops and tried to find that same unique note, and then they'd pull that and they'd breed that
Yeah.
together and they'd cross it and they'd proliferate that and try to breed that out again. Well, we can't maybe speed that up, but what we can do is um, provide more context. So if someone has these compounds in a neat format, they can smell these compounds and
Hmm.
become familiar with the scents themselves. And so
Yep.
now
Yep.
maybe if I know what octanoic and decanoic acid smell like, and I'm breeding tropical cannabis, and I start to smell, okay, this one has like this moldy kind of cheesy smell early on in the grow, like maybe that would help you know, like, okay, this one probably has these acids. It's probably not going to turn out as tropical as the rest of them. This is an outlier.
Right.
Or I know what indol smells like, and I really want to um, proliferate indol. So if I can get a good signature on my nose, I can go around and pick indol. So
Hmm.
it kind of just gives more information and context. I don't know that until we have access to this widespread, it will like change breeding.
Right.
But once we do have access to that, I think it's going to just kind of balloon and explode really fast because breeders are crazy. Like they are, so you have to be insane on some aspect to be able to deal with thousands of seeds and
Yeah.
provide them all the care and labeling and separating and all the trials and tribulations that go along with pheno hunting and
Yes,
chemo
yes.
hunting.
Hmm.
Mad props to them. Like without them too, we wouldn't have all of this unique exotic cannabis
Right, right.
now. And so I hesitate to say, like, now that we have this research, like we can take it to the next level. Like until this research is in people's hands, we're kind of limited by that. And I think it's just another example of science catching up after the
Hmm.
fact.
Yeah, yeah, yeah.
Um, and so I think in the future, when this is in people's hands, we will be able to answer all of those research questions really quickly. Like once
Yeah,
breeders are
yeah.
able to access this, we're so close to figuring out the genetic pathways that contribute to
Hmm.
this. We're so much closer to being able to calculate the phenotypic distribution of some of these compounds and the likelihood that you're going to have these offspring. So we're really just unlocking the door right now, and then once we're in the next generation of people having pretty much unlimited access to this, then we are like right now we're like loading the ship up,
Hmm.
and as soon as
Yeah.
they get ready to take off, I think it's going to happen so quickly. We're going to be inundated with all of this data that is just going to answer like questions like that and
Yeah.
that and that,
Yep.
because the fact that there are breeders out there who are sequencing their whole library already, and then
Exactly.
once they
Yep.
get this VSC data to be able to cross compare, like that's the kind of numbers we need to make significant claims based on this data.
Yeah, yeah, no, exactly. It's an exciting time because like even just get another example of how some of this data can be useful and sort of partner with other data. Think about once you start to understand the differences in flavorants and terpenes among plants and you have better analytical methods and better data, representing all of that, you can then start to correlate that to things like pest resistance and say, are there plants with certain chemical profiles taking these things into consideration that tend to be more resistant to certain things than others or perform differently than others? Um, and so starting to just correlate these aroma profiles with other aspects of the plant biology and sort of also the sort of chemical ecology around the plant that all of these compounds are contributing to is fascinating, and especially partnering that with machine learning and AI and stuff to really analyze huge data sets quickly. It does seem like we're like really close, really, really close to a lot of dominoes starting to fall and a lot of aha moments, kind of coming around where we can start to practically use all of this data rather than just sort of generating it for the sake of generating it, which is kind of the phase we've been in up to this point. And it's like we get a lot of testing done, mostly for regulatory purposes or for basic R&D and stuff. It's a lot of data generation, and it's only recently that now we're starting to think critically about that data, start to go back and look at it, figure out what we can do with it, and improve it. So yeah, I couldn't agree more. I think it's an exciting time in general for everybody and for so many reasons. Because this is an example of a trend in sort of cannabis research that's going on broadly. There's like just this tidal wave of all of this um, data coming together that provides so much low-hanging fruit in terms of research. It's like, oh my gosh, there's so many things now. And now that this doorway has been open, there's like a million things to look at. And then a lot of those sort of old questions to kind of get wrapped up as we move on to, the more sort of frontier um, of the research side of things.
Right. We're just playing catch up right now and just kind of filling out our toolbox and
Yes,
toolkit.
yeah.
And then, but I love what you said about pest resistance because I think we forget a lot of these compounds are generated for the plant to be
Right.
resilient. Like that's their entire purpose, is to keep the plant safe. And us as humans have like totally overlooked that, and we're like, oh,
It tastes good.
yeah, it smells good, exactly. But I think one practical application I can say of this research that's like a more immediate payoff is, I think this gives us a lot more tools to be able to provide accurate aroma descriptions to
Hmm.
customers and
Yes.
consumers. And so whether that is because people have access to lab testing that gives them more information that we can then generate a better description for consumers to utilize. And what that looks like, we could look at a bunch of different industries. We could look at the fragrance
Hmm.
industry,
Yeah.
and
Yeah.
the fragrance industry never says, oh, I have ethyl butyrate at 10%. The fragrance industry says light apple, rose,
Yeah.
jasmine, rain, like, things that people kind of can wrap their mind around. So whether it looks like that and it comes from data that is coming from a testing lab that is then translated into a
Hmm.
meaningful format, or whether it comes from people in the community who take it upon themselves to learn these skills,
Hmm.
be able to identify these different aromas in the plant. Because like I said, we've seen from this data, people have the ability to differentiate this
Yeah.
just as much as analytical equipment does. So if you train yourself, if a bud tender or patient advocate is especially knowledgeable in these compounds and the chemistry behind them, and does their due diligence, that
Yeah.
would benefit consumers.
Yeah. No, I totally agree. And to put this into context for folks listening or watching, in the like perfume industry, this is actually a common thing that happens. Like there are people who validate their noses against analytical equipment to to literally analyze smells with their nose. And there's like a standardized nomenclature for how to talk about the smells and the intensities and all these different things so that it can really get sophisticated. And that is a big issue right now is you know, a lot of times going back to this issue of, the top 3 to 5 terpenes being put on a label, people sort of get trained to think, okay, linalool's like lavender and limonene's like oranges or lemons and pinene is piney. And so then they see those top terpenes listed and then they make assumptions about what the aroma is going to be like, especially in states that have prepackaged cannabis like where I am right now. That's all you have to go off of. You'll never have a chance to smell the actual, product you're getting. And so a lot of people are jumping to that. Like, I like things that are more citrusy, so I must need high limonene. And it's like, well, what kind of citrus are you talking about that you actually like? There's more to that. Um, so yeah, this bridge between the data and actual aroma and that communication piece. It's more important than I think a lot of people give it credit for because, like I said, that's all some patients and consumers have to go off of. And we
Right.
know the nose is nose, right?
Absolutely. That's why, like, I am a big proponent for deli style
Hmm.
cannabis. I know that there's there's lots of controversy around it for regulators, but I think I think we have enough data and research at this point to show
Hmm.
that the aroma is as important as THC concentration to consumers, and that, you know, patients deserve access to knowing what they're going to have before they spend an absurd amount of
Hmm.
money on medicine. And if we look at other industries too, like, we would never expect people to make produce selections
Yes.
on
Right.
prepackaged vegetables, or, and we can't say that we have the same quality consistency as Coca-Cola manufacturers.
Hmm.
So why would I expect that every time I go buy Blue Dream from this farm that it's going to be the exact same? It just
Yeah.
doesn't make sense for what we have evidence of now. Like, there's the paper that's entitled The Nose Knows. There's the exotic papers. There's research that Anna Schwab has done. I feel like there's
Yep.
enough research on the sensory aspect to be validated and having deli style. And, I don't know that. And in California, terpene testing is optional for manufacturers. And so they don't even have to put, not that I think 3 to 5 terpenes is helping, but they don't even have to put anything about the aroma on there. And one thing we know from the first exotic paper is that we measured a strain. I can't remember what it was. I want to say it was supposed to be a sweet strain. Oh, it was supposed to be Gorilla Glue. And so that's a savory strain that it would have like those prenylated VSCs. It would be more fusel, but it had Tropicana sulfur compounds in it and lots of sweet compounds in it. So if you look on the label and it says Gorilla Glue, and then you get an orange citrus strain because the label was whatever they wanted to call it, like now we're just making it so much harder for consumers to know what they're going to smell when they open that lid. So I do think this research provides enough evidence to support that claim, in addition to all the other research that came before this on aroma.
Yeah, and focusing on aroma is one of the main thing that gets us away from strain names altogether, and, at least from the consumer perspective. When I've worked with patients, like that's one of the main sort of things we go through in our first several meetings is like trying all these different things to figure out like what aroma profiles are you generally drawn to, and do you tend to like come back to ignore the strain name, ignore the indica sativa labels, just focus on the overall quality of that flower and what you pick up on organoleptically. And so, if we want to move past strain names and indica sativa labels, then we have to bolster that side, the aroma side, and allowing patients and consumers to really assess the true quality of the products that they're getting. Like I said, I mean, this really applies to herbal cannabis, but like you said, I mean, you wouldn't force people to only have the option to buy their apples prepackaged in a way where you can't even see the apples before you get them, but you have a label that tells you they're red delicious apples, and you're like, okay, cool. And you buy them, and not only are they not red delicious apples, they're, Granny Smith apples or something, but they're also bruised. And it's like, that's the situation we're in with a lot of cannabis right now. And it's crazy.
I know it's hard to, like, as patients who love cannabis, it's hard to see that the like general population that their job is not cannabis research is being disserviced because we don't have the information out there and accessible. And so like that's why whenever I see like bud tenders who are like taking the time to get educated about it, like I really appreciate that, because I think like they're the first line of people that interact with new patients. And if I can only imagine if I was a new patient in this marketplace, how overwhelmed I would be and how upsetting it would be to try product after product after product, not knowing ever what I'm going to get, as someone who would be sensitive to that. But I do think like there are ways, like if you're interested, and I mean, and there are programs, we've seen it. There are programs that exist right now. There's like the Sewer, and there's interpening, and there's people who pride themselves on understanding cannabis aroma. And I really encourage all of those people to keep an open mind as this new research comes out, and like adopt it and look into it and learn about it and add it to your courses and add it to your toolbox so that you can help your patients better. Because if your job is to advise patients with aroma and you're not up to date on the new aroma chemistry, then I don't want to say you're doing a bad job, but maybe you should think about what you're trying to get out of your patient
Exactly.
conversations.
Right, exactly. It leads to a huge gap. And what do you think is so looking at what you've done so far and the findings that came from all of this, what's sort of on the horizon, what sort of questions are you left with now in terms of things that you're interested in kind of exploring further?
So I'm still super fascinated with cheesy cannabis. So that's
Yeah.
something that I'm keeping definitely like at the forefront. To because I think we really have just started cracking into the cheesy cannabis
Mm-hmm.
conundrum. I think that there are more compounds, and I think we can do a better job of explaining that pathway. And so what I need to analyze a ton of cheesy cannabis to
Yep.
see how it differs. But cheesy cannabis is kind of like a hard find in our area, and I think a lot of times when I see it, um, it does tend to be kind of tropical too. So there's
Mm-hmm.
like that duality to it too. So cheesy cannabis is definitely like something we're keeping our eyes peeled for on the horizon. Um, and then I think we are super interested in trying to uncover VSC pathways genetically, but you know, as a flavor house that specializes in analytical research, it's a little bit out of our wheelhouse. So
Yeah.
we're trying to collaborate with people in that aspect, but we'll just have to see how that pans out as the research goes on based on the sequencing end and our end. And then we have another paper currently in the works right now by my colleague Manny, and he's doing a really interesting paper that is going to talk about the composition of different hash extractions.
Nice.
Um,
Yeah.
and some of these he'll be talking about some of these compounds, but also some other compounds that aren't disclosed in my paper. So that will be really interesting. And then I think after that, I'm kind of switching up my area of research. Basically, we've gotten a really good set of tools in our arsenal to say, okay, we feel comfortable, analyzing the chemical data. We feel comfortable analyzing the
Mm-hmm.
sensory data and putting those two together. And so now we're looking at another third variable that we're not comfortable analyzing and trying to incorporate that into our data and see how that plays out. So we're looking into like some of the things regarding stability of these compounds, and
Nice.
so
Yeah.
that will be something that comes out much further in the future because stability takes a lot of time
Yep.
to assess, but that is kind of where we're going with this. And then in addition to that, we are also developing a 1D GC method that identifies a handful of these compounds, not all of them, but
Yeah.
some of the ones that we've deemed to be more important and that would have like more direct application for consumers. So we're working on trying to develop that 1D method and validate it against the 2D method. And then once the 1D method is validated, hopefully you will be able to find testing labs in your
Yeah.
area who are willing to, acquire the new materials needed to test for that. So we're hoping to, in the next like 1 to 2 years, try to push this out to people so that they can have access to this testing, because even if I wanted to test
Mm-hmm.
everyone's samples who wanted to send them to me just in the state of California, I could never do that by ourselves. So we want to get in touch with testing labs who already have some of that infrastructure and the right people on board to make it so that manufacturers and consumers can have access to this more high fidelity data.
Yeah. Yeah. No, absolutely. That's cool. The idea of validating a method that can go out to the testing labs. Because even if they weren't seeing, exactly all of these different compounds, they can still get a snapshot of, approximate total VSCs or something like that, if they have the detector for it, or you can see, for instance, because I know just from doing some of the GC work that I've done, the fatty acids you can see on there, as long as you can get the separation. Um,
There are esters you can see in there
mhm,
too. And I mean, it's not that I think it's like, it's something that is definitely doable and labs can do, but from our experience in the industry, it's not something that probably will be prioritized heavily.
right.
And because method development is so time and resource consuming,
Hmm.
we want to remove that barrier so that labs can just hit the ground running, which is what they need to keep up their throughput
Hmm.
and honestly just to stay afloat. That's what they
Right.
need, not even to turn a profit. They just need that help. So we that's what we want to do at Abstrax, to like, not because it's great that we have the research, but we understand that the value is in the industry having this
Yeah.
capability.
Yeah, I mean, it'd be great to one day see the methods that abstracts are using as, validated AOAC methods that testing labs could simply just choose, verify, because that shortens the process a lot right there. Just knowing that, like, oh, here's a method. Because a lot of, just for people that aren't familiar, when testing labs are choosing their methods, they usually have to choose methods that weren't even validated against cannabis products at all. And then they have to sort of revalidate them for those matrices. But if you had methods that were originally validated on cannabis extracts and on cannabis flower, that would be immensely valuable to testing labs because then they wouldn't have to do full revalidations. They can just do what's called a verification, which is way simpler and faster to do, just to say, okay, if we do what this method says, yes, we get the same answers reliably. And that also would make it where regulators could then start to have some expectation too of what kinds of terpene methods, if they're going to require terpene testing for regulatory purposes, what sort of methods, are we talking about? What sort of level of fidelity sort of the data are we really talking about, that we're trying to require? So no, that's really cool. I hope that all works out. That's definitely a very good and noble path forward. I mean, like I said, that's the cool thing about abstracts is the constant education and sharing and trying to make this all available. And for also anyone that doesn't know, if you have consumed vape pens from any number of outlets in the past like several years or so, you've almost certainly consumed some of Abstract's products because there are tons of companies that use them. You don't always know like which vape pen manufacturers or edible manufacturers and stuff are using Abstract's products. But I know just from poking around in the labs, they show up quite a lot. So it's really cool to see. And I know I've kept you for like an hour and a half here. So we'll start to wrap up now. But thank you so much for being willing to, kind of lay this all out on here and explain, not just the research you did, but sort of all of the history that comes before and then sort of the frontier ahead. I think it's very exciting, and hopefully for anyone that's involved in this, either on the chemistry side, the analytical side, the formulation side, or whatever, there's a lot of areas here to work together and to do some cool things and move the industry forward. So as we wrap up here, I want to give you a chance to let everybody know how to follow your work, stay in touch with you, follow Abstracts, anything like that. Anything else that you kind of want to share as we wrap up here? I'll give you the floor to close out.
Thank you. Thank you so much for inviting me on, Jason.
Yeah.
I love talking to you. You're one of my favorite interviewers, honestly.
Thank you. I
Um,
appreciate that.
yes, and I just love talking to you. But you can find our white papers, which are like more simplified version of all
Hmm.
of our peer review research papers, on our website at abstractstech.com. You can find me on Instagram at Twinkadink, and you can follow all of our socials on Instagram at Abstracts with an X Tech, or Abstracts Labs. And yeah, if there's any research collaborations or or collaborators out there that are interested in working with us, you please feel free to email Abstrax. And, we have an R&D email, rnd@abstraxtech.com, or you can reach out to Jason